Okay, we have a probability practice final exam. It is calculus based, so that'll be towards more the middle. Here we go with number one. Box contains 5 red, 4 blue, and 3 green balls. 5 balls are drawn without replacement. What is the probability that exactly 2 are red? What is the probability that all 3 colors appear? What is the probability that the 5th ball drawn is green? So we'll start here with letter A, exactly 2 red and 5 draws. Well, we would set that up using our combination formulas, binomial coefficients. So that's going to be the product of 5, 2, 7, 3 over 12, 5. Simplifying that, this could be 175 over 396. So again, this assumes that you've taken a college level calculus probability course. You've been through all of this, that you're familiar with the prerequisites. So I'm going to go through this rather quickly so it's more of a reference for you as a supplement to studying. So again, I'm going to go through this rather quickly. Letter B. What is the probability that all 3 colors appear? So here are possible color counts with 3, 1, 1 and 2, 2, 1. In this situation, use a complement probability of all 3 colors. Let's see what we have here. Only red, blue, 9, 5. Only red, green, 8, 5. Only blue, green, 7, 5. Okay, using our combination formulas. And again, I'm just going to pronounce through this quickly. Subtract your single color cases already included. So here's going to be the numerator over that 12, 5. And you're going to come out with your P is 295 over 396 when you simplify. Okay, you could change that to a decimal as well. And for letter C, what is the probability that the 5th ball drawn is green? Well, for this, by symmetry, the probability the 5th ball is green is just the fraction of the green balls, and that's 3/12, 1/4. Okay, so that takes care of number 1. So, move along. Sorry about that. Old-fashioned setup here. Number 2. Okay, so number 2. Let's see, get that in focus. There we go. Okay, a machine produces parts. Okay, part quality depends on the day's calibration. Okay, first bullet point there is on 70% of the days the machine is well calibrated and 2% of the parts effective. Second bullet point there is on 30% of days the machine is poorly calibrated and 12% of parts are defective. A randomly selected part is defective. Part A, what is the probability the machine was poorly calibrated? So here's what we'll do. Part A, we're going to let W equal well calibrated, P equal poorly calibrated, and D equal defective. Okay, and then we have P of W, probability of W here is 7/10. Probability of P is 3/10. Probability here of the D with the condition W, 0.02, and the D condition P, okay, we have 0.12, okay? And again, that's likelihood of the event occurring. Given that the other has occurred, I'm just going to put, say, conditional, because this is conditional probability. So for part A, this is Bayes' theorem. So we use Bayes' theorem, okay? And we're going to find P of D, right? So we find P of D. Okay, we're going to use this formula here to find P of D. We're going to substitute the quantities we know into there. And we're going to get 1/20.05. Okay, so therefore here, we have this P probability of that condition. That's going to be 0.12 times 0.3 over 0.05. So the probability there of that P, or the likelihood of P occurring given that that D has occurred, is 0.72. All right? That takes care of part A. Part B, if two randomly selected parts from the same day are both defective, what is the probability the machine was poorly calibrated? So, two parts defective, we could do this. P, probability, this condition, these conditions. Set up your formula again. There's a numerator and a denominator. Okay, and assuming independence is conditional on the calibration. Okay, for this B, D sub 1, D sub 2, in this condition P, you get 0.12 squared. P, D1 sub 2, condition W, 0.02 squared. So, putting this all together, here's our setup there, that P condition D sub 1, D sub 2 is going to be 0.12 squared times 0.3 over the denominator. 0.12 squared times 0.3 plus 0.02 squared times 0.7, which is going to give you this 108 over 15. Okay, 108 over 115, and we could reduce that. We could write that as a fraction. We could we could write that as 0.939. That's a 0.939 there. Okay, that's all for this one, number 2. Okay, so moving along. That's number 2. Now let's move on to number 3. And again, we're going to go through these quickly because this is more of a reference for you. Okay, so number 3, let X have probability mass function given here. Part A, we want to find C. Lowercase c, here's what we do. The probabilities must sum to 1. Okay, so what we're going to do is we're going to have C times 1 plus C times 2 plus C times 3 plus C times 4. That's going to equal 1. So, in this situation, we'll set 10C equal to 1. Divide by 10, C is 1/10. Okay, letter B, find the expected value. Okay, so that expected value there is going to be the summation of this, Kp, where X is K. So, we're going to take our values here. So, it's going to be 0 times 1/10 plus 1 times 2/10 plus 2 times 3/10 plus 3 times 4/10, and that's going to reduce to 2. Okay, so variance here, expected value of x squared, we'll do 0 squared times 1/10 plus 1 squared times 2/10 plus 2 squared times 3/10 plus 3 squared times 4/10. Okay, so this is just going to come out to 5, right, for the e to the x squared. Okay, now the variance, and that should technically be in parentheses. My apologies for the brackets. Should be in parentheses. Could be in brackets. Some people use brackets, but some use parentheses. So equals e, that x squared, minus e x, that expected value, the whole thing squared. Okay, so these are two different things, right? You've probably seen this before a bunch of times. So the variance is going to be 5 minus 2 squared. Just substitute what we had here, 5 and the 2. This gets squared, and that's 1 for the variance. Okay, letter D, we want to find the expectation value there, expected value of x minus 1 squared. So what you do is, first we'll expand it. After expanding, we could write e x squared minus 2ex plus 1. And we just substitute what we know for that x squared and that e, that expected value for x squared, and that expected value for x. And we just get 5 minus 2 times 2 plus 1, and we get 2. Okay, so that takes care of number 3. Moving along. Number 4. Okay, continuous random variable. Okay. For number 4, a continuous random variable has that given density. For part A, we want to find k. So, for this, A density must integrate to 1, so we set this up, set up your integral, and there are integration steps. Again, I'm just going to go through this quickly. Just using our calculus, we're going to get 32 over 3k equals 1, and k would equal 3 over 32. Okay? So we could use that information to help us with part B and part C and part D. So for part B, they want to know the probability of 1 being less than x being less than 3. So in order to do that, set up an integral again. From 1 to 3 are our bounds, our limits of integration. So on these bounds, 1 to 3, we use that k, 3 over 32, times the function x times 4 minus x dx. Okay, integrating here with respect to x. Doing our computation, we come to the result of 11/16. Okay, for letter C, we want to find the expected value. To get the expected value, we are going to integrate again. Here, we're going to integrate from 0 to 4, x f of x dx. So, x times that integral we had here. So, basically, it's just integration there in terms of one variable. Integrate, we wind up with the value of 2 for the expected value of C. And for letter D, we have the variance. Okay, so to get the variance, we have the expected value of x squared. So we integrate from 0 to 4. And this time, instead of x, f of x dx, it's going to be x squared, f of x dx. Same thing, integrate, perform the computation. Okay, we're going to get a 24 over 5, right? And now we could get the variance by saying the variance of x is the expected value of that x, right, squared, minus this e of x, that expected value, squared. Okay, so these two, again, are different things. Pardon me if I spoke too fast and possibly miscommunicated, but this is what should be written. And just substitute 24 over 5 minus 4. That gives you 4/5. So that takes care of number 4. Okay, that's 4. And now let's move along to number 5. Okay, so for number 5, let x have cumulative distribution function given here by this piecewise function. Part A, let's find the density of f of x. So to do that, find this density. The density is the derivative of the CDF, the cumulative distribution function. So we just take f prime, and we take it here for x squared over 9. Okay, because it exists there. The other two derivatives are 0. You get 2x over 9 for the domain 0 is less than x is less than 3. So we could write that as f of x equals 2x over 9 for the domain 0 is less than x is less than 3, and the output values will be 0 for otherwise. For part B, probability of x is greater than 2. Probability of x is greater than 2. It's going to be 1 minus that f of 2. So it's just going to be 1 minus 2 squared over 9. And you're going to get 1 minus 4 ninths, 5 ninths. Okay? Letter C, find the median of x. So what we could say here is the median m satisfies f of m equals 1/2. So we could set this up as m squared over 9 equals 1/2. Solving for m, we get plus or minus 3 over root 2, but we take the positive 3 over root 2. And if you want to rationalize the denominator, it could be m equals 3 root 2 over 2. For part D, find the expected value of x. So, expected value of x here, integrate from 0 to 3. And that's going to be x times the 2x over 9 dx. Using our integration, okay, we wind up with 2. So 2 is our expected value here. Okay, moving along. Number 6. Okay, so number 6, we have the following. We have, whoops, sorry. Let x have joint density given by this f of xy, so we have two variables now. This c, x times quantity x plus y, domain 0 is less than x is less than 1, and we have 0 is less than y is less than 1, and our 0 otherwise. Now we want to find c here. So what we want to do here to find c is the total integral has to equal 1. Okay, so we set that up and we're going to integrate respectively. Okay, first with dy, set this up, we're going to get x plus 1/2, c on the outside, and now with respect to dx, get that 1. So it's going to be, technically, after we perform the integration, it's going to be c times the sum of 1/2 plus 1/2. That's going to equal 1. So c equals 1. Okay. For part B, find that marginal density here. So to set this up, that f subscript x of x, we're going to integrate from 0 to 1 of f of xy dy. F sub x of x equals 0 to 1 x plus y dy. So it's going to be f subscript x of x equals just the x plus 2 on from 0, the interval 0 is less than x is less than 1. Okay. For part C here, we want the probability of x less than y. So to set this up, probability of x less than y, we're going to have our bounds of integration here 0 to 1 and 0 to y respectively for dx dy, quantity x plus y. Okay, first integrate with that right here, the inner integral from 0 to y. Okay, we wind up with y squared over 2 plus y equals 3y squared over 2. Okay, and now let's see what we have here. From 0 to 1, 3y squared dy. Now we're doing dy. And that comes out to 1/2. So that would be letter C, would be 1/2. And letter D, our x and y independent, explained. So here's what we could say for this. For f subscript y of y, f subscript y of y equals from 0 to 1 integrated for x plus y dx. So with respect to x, you're going to get 1 over 2 plus 1 y. That's y plus 1/2. And if they're independent, then f of xy equals f subscript x of x, f subscript y, y. However, what happens here is that product, f subscript x of x times f of subscript y of y, that equals this, x plus 1/2 times y plus 1/2. Okay, from substitution, this is not equal to x plus y. Since it's not, we could say x and y are not independent. So that would be a no for letter D. Moving along. Okay, moving along here to number 7. So number 7, let x have density f subscript x. X equals 2x. 0 is less than x is less than 1. And we want to define this. This is y equals negative natural log of x. So negative natural log x. Find the range of y. So since 0 is less than x is less than 1, then this log of x is less than 0. So negative log of x has to be greater than 0. And that comes down to, well, y would have to be greater than 0. Letter B, find the density of that y, solve for x. We isolate this, take the natural log. Okay, here we substitute, and x equals e to the negative y. Okay, so now what we do is we employ the transformation formula. The transformation formula here, that f sub y script of y equals f subscript x of that e to the negative y, and now we're differentiating x with respect to y. Absolute value of that derivative. X equals e to the negative y. So dx dy is negative e to the negative y. Okay? And taking the absolute value, it's now e to the negative y. So therefore, we could say f subscript y of y equals 2e to the negative y times e to the negative y. So that's a 2e to the negative 2y, where y is greater than 0. Okay, so here this y, we have an exponential of 2. So it's distributed as 2, exponential 2. In letter C, we want to find the expected value of y. So here, for an exponential random variable with rate 2, so it has a rate 2 from letter B, we're going to get 1/2 that expected value of y. Okay, so that takes care of letter C. Okay, and moving along now to number 8. Okay, so number 8, the lifetime t in years of a certain electronic component is exponential with mean 5 years. Okay, so find the parameter lambda. So for an exponential random variable, this expected variable of t, expected value of t equals 1 over lambda. Okay, so 5, set it equal to 1 over lambda, and 5 lambda equals 1. We wind up dividing by 5 lambdas, 1/5. Okay, for letter B, find probability of t is greater than 8. For an exponential random variable, that probability, capital T, is greater than lowercase t is e to the negative lambda t. So the probability of t greater than 8, that's going to equal e to the negative 1/5 times 8, substituting. So that probability is just going to give you e to the negative 8/5. All right. So just moving along here for letter C, find the probability. You're given this condition, t greater than 10, condition t greater than 4. And this probability here is going to be the probability of that difference, t is greater than 6. And that's by the memoryless property. Okay? So, according to the memoryless property, we can now say p of t is greater than 6 equals, substitute for that base e, negative 1/5 times 6. That's all. Think about where that just comes from. Previous information. So e to the negative 6/5. Letter D. Explain briefly what property is being used in part C. Well, in part C we mentioned it. It's the memoryless property. And this winds up equal to probability of t is greater than lowercase t. Okay, so that takes care of number 8. Okay, so moving forward, let's now do number 9. Or go through number 9. Okay, so here's what we have for 9. We have suppose test scores are normally distributed with mean 76 and standard deviation 8. Okay, so part A, what is the probability that a student scores above a 90? So this is a pretty standard problem. So the scores are normal. Okay, mean 78, standard deviation 8. So for probability of x is greater than 90, standardized, take our z equals that x minus the mean over the standard deviation. So 90 minus 76 over 8, that's going to give you 1.75. So now, probability of x is greater than 90. That's going to be the probability of that z is greater than 1.75. And if we go and use a standard normal table, if you just go and look that up, that probability of z is greater than 1.75 is approximately 0.75. 0.0401. For part B, what score is the 90th percentile? Well, the 90th percentile has z sub 0.90. That's approximately 1.2816. So x equals that mean plus z standard deviation. Substitute at 76 plus 1.2816 times 8. And we're going to get x equals 86.2528. X is about 86.3. Okay. And for part C, if 36 students are selected, what is the probability their sample mean exceeds 78? So for n equals 36 here, what we could say is this x bar, okay, and this is our sample mean, right? And it's being distributed as, or follows the distribution of 76, 8 over square root of 36. So that's 76, comma 4 over 3. So the sample mean probability of that is greater than 78. We standardize this. We get z equals 78 minus 76 over 4/3. That gives us 1.5. So the probability that the sample mean greater than 78 is equal to the probability of that z greater than 1.5. And we check table. We get 0.0668 for number 9. Okay, so that takes care of number 9. Moving along. So now we have number 10. Okay, so for number 10, we have a random. Okay, for number 10, we have a random variable x has a moment generating function. Okay, that's what we're given here for our moment generating function. All of this. And t is less than 1/2. So for part A, they want you to identify the distribution of x. So this is the MGF of a gamma distribution with shape 3 and scale 2. So this x, right? This x is distributed or follows the distribution of the gamma where alpha equals 3 and theta equals 2. So the rate is going to be just lambda equals 1/2. So for letter B, find that expected value of x for a gamma random value. This expected value of x. What's that going to be? That's just going to be the alpha minus, that's going to be the alpha times the theta. 3 times 2 gives you 6. Okay. For part C, we want to find that variance of x. Well, the variance is just going to be alpha times theta squared. So 3 times 2 squared, that's going to give you a 12. Okay, in part D, we want to find m subscript 3x plus 1 of t. So for y equals 3x plus 1, we get m y subscript y of t equals that expected value of e to the t times 3x plus 1. Okay, and then just doing the computation here. Okay, separating the, breaking this up. This is going to be m subscript y of t equals e to the t, m sub x of 3t. And m sub y of t equals e to the t, substituting this, what we have here, substituting this as 1 over 1 minus 6t cubed. Okay. And now for here, what we have, m subscript 3x plus 1 of t, that's going to just, if we want to write it with a negative exponent, e to the t times the quantity 1 minus 6t to the negative third. Okay, so that takes care of number 10. Now we can move along to number 11. Number 11, let's see what we have here. Okay, Poisson, so let x, there is distributed Poisson 4, and y is distributed as 7, Poisson or Poisson 7, independently. So for part A, we want to find the distribution of x plus y. So the sum of independent Poisson random variables is the following. So we have Poisson here, that x plus y is distributed as Poisson 4 plus 7, and the x plus y distributed Poisson 11. For B, find the probability x plus y equals 10. So we would use the formula. I didn't write it down, but you might be familiar with this, or you could look it up. This would just be e to the negative 11 times 11 to the 10th over 10 factorial. Okay, that's just a formula there we're applying. Part C, find the expected value of the sum of x plus y and the variance of x plus y. So in this situation, for a Poisson random variable, that expected value of x plus y, that's just going to be 11. And in this case, also the variance is going to be 11. For part D, given x plus y is 10, find the probability x equals 3. So binomial distribution. X has a binomial distribution, and we could have this x, the condition x plus y equals that 10 distributed as that binomial of 10 4 11ths. Okay, so that's a 10 comma 4 over 11. So this becomes probability of x equals 3, that condition x plus y equals 10. And then we have these. Here our combination formula is 10, 3, 4, 11 to the 3rd, 7, 11 to the 7th. And I just left it like that. Okay, so that takes care of number 11. Let's move along now to number 12. Okay, so number 12, that n is distributed as a Poisson of 6. Given n, capital N equals lowercase n, let that condition that xn equal the n distributed to that binomial lowercase n comma 0.4. Okay, so for this, here's what we do for part A. Find that expected value. So we're going to use the law of total expectation. So that's going to be that expected value equals E, bracket, E, and this x condition n. And since E, this x condition n, that equals 0.49. Okay, I'm sorry, 0.4n. And now E of x equals E of 0.4, E times 0.4n, that expected value rather, equals E times that. So E of x equals 0.4 E times n. Substituting that expected value is just going to be 0.4 times a 6. So that's just going to be a 2.4 for the expected value. Okay, so and that's just substitution there at the end. Part B, find the variance of x. So for now, we use the law of total variance. Here's the law of total variance here. I won't read it out. Okay, it's a little wordy, but you've probably seen it before a bunch of times. So variance of that x condition n, just substitute that would be n times 0.4 times 0.6. That's going to give you 0.24n. And now the expected value, the variance of x condition n, we get E at expected value of 0.24. Okay, so that's going to be times n. So that's right here, 0.24 times 6. So 0.24 times 6, that gives you just 1.44. Okay, so we're going to need that information later on. So now, and that expected value of x condition n, that's 0.4n. So the variance of the expected value x condition n, that's equal to the variance of that 0.4n. So 0.16 variance of n what we could say is since n is distributed as Poisson of 6, the variance of n is 6. So the variance here of the expected value x condition n, that's 0.16, and times 6, that gives you 0.96. So to get that variance of x, which we wanted up here, we take that 1.44 and add it to 0.96, and we get 2.4. Okay? So that's part B. Part C, identify the distribution of x. Well, this is Poisson thinning, so that x is distributed as Poisson 6 times 0.4. So that's x distributed as Poisson 2.4. So that takes care of number 12. Moving along, 13. Whoops, sorry about that. So, 13. Let x sub 1, x sub 2, dot, 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 x sub 5 be independent random variables uniformly distributed on the interval 0 to 1. Let m equal that max x sub 1 all the way to x sub 5. So, for part A, they want us to find the CDF of m. Okay, f sub m of m equals probability of capital M less than or equal to m. So, the maximum is less than or equal to m. Only if all 5 variables are less than or equal to m. That should be a 2m. Okay? So, what we could say here is that f subscript capital M of lowercase m, that equals the probability of x sub 1 less than or equal to m raised to the 5th. By independence for 0 is less than or equal to m is less than or equal to 1. So f subscript m, capital M, of m, that's going to equal m to the 5th. So if we want to write this as a piecewise function, that's going to be f subscript capital M of m equals this piecewise 0 condition here. M is less than 0, m to the 5th, where 0 is less than or equal to m is less than or equal to 1. And 1 where m is greater than 1. For part B, we want to find the density of m. Okay? So, we found the CDF of m and a. To find the density, what we do is take the derivative. So we differentiate the CDF. So, differentiating this CDF, okay, the 0 and the 1, well, if you try to differentiate those are constants, they go to 0. So this component here, the m to the 5th, differentiate that, okay, and now that becomes, I'll use a lowercase f m, capital M of m, of lowercase m, that equals 5m to the 4th, and from 0 to m, from 0 is less than m, is less than 1. Okay, letter C, we want to find the expected value of m. So the expected value of m, what do we do here? We take the integral from 0 to 1, m times f subscript m of m dm. Okay, so that's 5 from 0 to 1, m to the 5th dm. Integrate, and we're going to get 5/6. Okay, part D, find the probability of m is less than 0.8. So, probability of m is less than 0.8. F subscript m of 0.8 is 0.8 to the 5th. And that's 4/5 to the 5th. 1024 over 3125, which is about 0.3277. Okay, so that takes care of number 13. All right. Number 14, let's see here. Let's get this in focus. Okay. 14. All right, a factory produces bolts whose weights have a mean 50 grams and standard deviation 4 grams. Sample of 64 bolts is selected. Approximate the probability that the sample mean is greater than 51 grams. Okay, let's do part A first, right here. So the weights have a mean of 50, standard deviation of 4, and n equals 64. So the sample mean has an approximate distribution. That sample mean is approximately n, parentheses 50 comma 4 over the square root of 64. That's just using the formula. So 4 over square root of 64, 4/8, that's 0.5. And the probability of the sample mean greater than 51, that will be equal to the probability of z greater than 2. So we standardize this. Here's where the 2 comes from. We standardize this. The z is 51 minus 50 over 0.5. That equals 2. So these are just based on formulas, textbook formulas, stuff you do in standard probability course. So that's where the z comes from. And basically, we're going to get 0.0228. Okay, so when we let's move on to letter B. Okay, let the total weight be the following here. So for letter B, approximate the probability that the total weight of the 64 bolts is less than 3,180 grams. So for part B, we'll let the total weight be S equals x sub 1 plus ... plus all the way to x sub 64. So that expected value of S, that's going to be 64 times 50 equals 3,200. And let's see the standard deviation. So that's square root of 64 times 4. 8 times 4, you get 32. We want the probability that that S has to be less than 3,180. So when we standardize this, we use our z. So that's just going to be that difference, that 3,180 minus 3,200 over 32. We're going to get z as negative 20 over 32, which gives us a negative 0.625. So our probability here, S is less than 3,180, which is equal to the probability of z less than negative 0.625. And if we look that up, that would be 0.266 for letter B. Okay. And for part C, we want to explain why a normal approximation is reasonable. Okay, so what we could say here, a normal approximation is reasonable because the sample size is fairly large. Your n is 64. Okay, so by the central limit theorem, the distribution of the sample mean and the total is approximately normal. Okay, so that was number 14, and now number 15 would be the most time-consuming one. I'm going to go through this quickly, though, so you have this as a reference, and this is something to, try on your own and use this as a reference. I'm just going to go through this quickly, but this would take some time to do. So this is like a challenge-type problem. So number 15. Let x and y be independent exponential random variables with rates lambda and u, respectively. Part A, let's do first, find the probability that x is less than y. Okay, so here's what we can do. So for part A, let x, right, it's distributed as the exponential lambda, and let y distributed as the exponential u, independent. We want P is probability of x less than y. We want it on the condition that capital X equals lowercase x. So what we can do here, this is the probability of x is less than y. We can integrate an indefinite integral here, 0 to infinity. Probability of y is greater than x. F subscript x of x dx. Okay? Moving along here, since our y is greater than x, that's equal to e to the negative ux, and f subscript x of x equals lambda e to the negative lambda x. So our probability of x is less than y, that's going to be equal to the integral from 0 to infinity e to the negative ux, lambda to e to the negative lambda x dx. Okay? Okay, it's just doing some computation. taking out the lambda, 0 to infinity, e to the negative quantity lambda plus u x dx if we go ahead and integrate that. So you could try that on your own if you want to. That comes down to lambda times 1 over lambda plus u equals lambda over lambda plus u. Okay, so that takes care of letter A. Again, I'm just going through this fast so you have a reference if you want to try this problem, and you have the steps here. I omitted some steps because you could do that on your own. You might be able to do all these on your own. A lot of you already probably very, very proficient with probability. Part B, z equals m of xy. Find the survival function. Why do we want to do that? Well, for part B, they're telling us to find the density of z equals the min of xy. So if they're telling us to do that, okay, we want to find the survival function. So take the probability of z is greater than z. Probability of minimum of xy is greater than z. This means both x and y exceed z. So the probability of that capital Z greater than lowercase z, okay, that equals the probability of x is greater than z, y is greater than z. Now, by independence, the probability of that capital Z greater than z, lowercase z, is equal to probability of x is greater than z, probability of y is greater than z. So what that's going to come out to is that, again, e to the negative lambda z times e to the negative uz. Putting these together, you get e to the negative lambda plus u times z. So we could say z is exponential with rate lambda plus u. Okay? Letter C, we want to find the expected value of z. Well, luckily for this, as a segue from B into C, since that z is distributed as exponential lambda plus u, our expected value of z is 1 over lambda plus u. Okay. And part D, find the probability of this condition x less than y, where condition z is greater than t, where t is larger than 0. So right here, we want probability of x is less than y, condition z is greater than t. So the event z is greater than t means both variables have survived past lowercase t. So x is greater than lowercase t, y is greater than lowercase t. So we could say here, by the memoryless property of exponential random variables, after time t, the remaining lifetimes are still exponential with the same rates. So the probability that x finishes before y is unchanged. So we wind up with the probability of that x is less than y, condition z is greater than t. That's going to equal lambda over lambda plus u. All right, so that's it, 15 problems. This serves as a reference, just hopefully as a supplement, as to help you get more practice before a probability exam. All right, thank you very much and have a great day.